Okay, so today we have the test, of course, which will be right after my initial sort of discussion. But for this week, my plan is to finish up our discussion of oracles and Dutt-Jozsa algorithm. I realized that it's not too hard if you understand the Dutt-Jozsa to do the Bernstein-Vazirani, and then we'll do the Simon's problem as well this week. Probably won't spend as much time on Qiskit, but I decided that one thing I can do is I finally figured out how to run it on my machine, and also I put it on a GitHub. So what I'll do is I'll share the GitHub link with all of you, and you can follow along with the code over there. Okay, so today, so in the last class, we showed that an identity which is called phase kickback identity. And the reason that this identity is useful, we'll see an example of it when we solve the Dutt-Jozsa and the Bernstein-Vazirani and the Simon's problem. They basically all use this idea. So the idea is that if you have Q0 and Q1, and both, if initially they were both in Hadamard, if you put a Hadamard, they would both be in the plus state, right? The one would be in the Q0 would be in the plus state, Q1 would also be in the plus state. And then if you applied a C0 gate, nothing would really change because you would just still get back the same state, because C0 just flips 0, 1 to 1, 0 and 1, so that it doesn't change the overall phase of that state, and therefore the state remains the same. But if I now add a NOT gate in front of Q1, now this state has become the minus state. So the state that we would read now would be minus and then plus. So this is this would be the minus state because it's the bottom qubit, and then the plus, so it would be minus plus, right? That's how we read it. And then when we apply the C0 gate, we find that the minus state gets kicked onto the state Q0 as well. So the output after all this is minus on the output. So this is an example where the control qubit gets modified by the action of the target qubit, so by the phase of the target qubit. So that's why we call it phase kickback. And we proved this identity in the last class, so I won't discuss it again, but that's the basic idea of this. And this actually comes from another identity we proved quite a while ago when we were discussing gates, which has to do with interchanging the action of the control and the target. So if I take this C0 gate and I surround it by Hadamards on both sides, Hadamard here, then that is equivalent to a C0 gate with the control qubit being the left qubit and the target qubit being the right qubit, okay, or the left qubit being the bottom qubit and the target qubit being the top qubit. So that because of that identity is why we get this phase kickback, basically. All right. So we discussed the quantum oracle last time. I presented it for the particular case of the Dutt-Jozsa problem, but this is just the most generalized version for any oracle. Okay. So any oracle basically corresponds, or every classical oracle is basically a query. You're writing to a query to some circuit or some function. Let's call that oracle f of x. So what it does is it takes, in this case, it's for 1 bit, but it could be n bits, for example. And this 1 bit oracle basically produces f of x, which is the function that we are trying to execute on that on x. And then we have the y, and then as we have shown you at the very beginning of the semester, we can always make everything reversible by adding this y and then taking the x off. So it's pretty much any classical circuit you take, add 1 more bit or n number of bits, depends on the context, but let's say 1 more bit, and then XOR it, and you can make it reversible. Okay? Yes?
So is the quantum oracle, is that just like a black box of a function? You just like
the
oracle?
I'll show you an example on the next slide. Okay. Or we'll do an example. And yes, and so then the quantum oracles are simply the reversible version, essentially taking this and implementing the circuit in quantum logic gate. Okay? And I'll show you an example now. And yes, you're right. So it's basically just a unitary matrix. That's what it is. So we just have to construct the right unitary matrix. And of course, in a real quantum computer, we may have a unitary matrix, which is all well and good, but in reality, what we need is some sequence of gates that we know how to do on that quantum. And that can take a little thought. We went through an example last class of a balanced oracle for the Deutsch-Jozsa problem, but for every situation, it may require a new construction, because the unitary matrix changes depending on the oracle that you're constructing. Okay, so we did one example last class, which was quite complicated, I thought. So I decided to simplify even further, just to give another example. This is essentially taking a classical oracle, which is very simple, right? It's a NOT gate. Okay. What is the equivalent quantum oracle? So let's do that example right now. So the oracle f of x, the classical version is not of x. Okay, and we want to construct the classical or the quantum oracle. So to do that, we need, of course, x, and then we add in our one more bit, y. Okay, as I've said, we always add in a bit when we want to make this quantum oracle. And so now we have four cases, right? 0, 0, 0, 1, 1, 0, and 1, 1. Okay. And the output is x, x, and then y plus f of x. Right? That's what our output is in all the oracles. Okay, so that's all we have to do now. So the output here is 0 for x, and then y plus f of x is 0 plus 1, so that's 1. Right? And then here, this is 0, 1, okay? And then when I take the naught of 0, I get 1, so 1 plus 1 is, or this one is of course 0. And what is 1 plus 1? Or in XOR language? Huh? 0. 0, yes. Exactly. Okay. And then we have 1. Okay, so we've got 1 here and 1 here. Let me just put those down. And then we take 0 plus naught of 1, which is 0. So 0 plus 0, which is 0. And then finally, we have 1 plus, again, naught of 1, which is 0. So 1 plus 0, which is 1. Okay. And from this, we can also read off, this is the oracle right here, right? And so from here, we need to construct the unitary matrix that carries out the transformation. So what is this transformation telling me? If my input qubits are 0, 0, right? They go on the output to 0, 1. Similarly, 0, 1 goes to 0, 0. 1, 0 takes me to 1, 0. And 1, 1 takes me to 1, 1. So what is the unitary matrix corresponding to this oracle? How do I go about constructing that unitary matrix given this transformations? Anybody? Yeah, yes.
You can start with row by row.
Yes, very good.
Start with like that's 1, 0, 0,
0,
0.
0 goes to 1.
Yeah, so it's 0, 0 goes to 0, 1.
So what should I write here?
0, 0, 0.
You want 0, 0, 1, 0? Is that what you're saying?
0, 0. This is 0, 1. So, sorry, 0, 0.
Very good. Good.
Oh, okay.
Let's go through it. Yeah, that's okay. What do you think should happen?
You take column vector 1, 0, 0.
Yes, column vector. Very good. And the column vector here is the input is 0, 0. So this is the first column vector, right? And in this column vector, the component along 0, 0 is 0. So the first element is 0. Component along 0, 1 is 1. component along 1, 0 is 0. Component along 1, 1 is 0. Does it make sense?
Yeah.
Okay. And then what about the next one? Anybody else? 0, 1 to 0, 0. Yes.
The next call will be 1, 0, 0, 0.
Very good. Excellent. And then what about the next one? Yes.
0, 0, 1.
0, 0, 1, 0. The last one? Yes.
0, 0, 0, 1.
Yes. Excellent. So that's it. Okay. So that's our unitary matrix for the quantum oracle. And now the question is, how do you construct it out of gates? What do you think? How can I construct this oracle from gates? What gate could I use possibly? Maybe start by identifying some familiar blocks, right? There are some blocks here, some blocks here. So it kind of looks like something. Yes,
X gate.
an X gate and an identity, but the X gate appears only in this corner, right? Not on every block. So yes, it's not quite a control node. That's correct. Yeah, but it's flipped. Exactly. Okay. So we'll have to add an extra X gate basically, and then that. Okay. All right. I'll let you figure that. That's. It's a good exercise, right? Every time you see some matrix, so think about, okay, how might I construct that? All right. So that is it for our example. Any questions on this? On what oracles and quantum oracles are? Good. And now that we have constructed the quantum oracle, let's now introduce the phase oracle. Okay. And actually, we have sort of introduced it, but I didn't make it so mathematically explicit already. So it's a good idea to like go through it now. So, so you saw we changed the target qubit to y plus f of x, right? That was our oracle. That's what our oracle did. It took the answer or target output qubit y and converted it to y XOR f of x. Instead, we can leave the output qubit unchanged and multiply the input qubit by a phase as follows. Okay, so let's go through that. So we've prepared the output qubit in the state, instead of preparing it in the regular 1 or 0 state, which is all a classical oracle can do, right? A classical oracle can only have input as 0 or 1. But now we're going to prepare the input, that is what I call the target qubit or output qubit. I always have to say this carefully. So the output qubit or answer qubit, let's call it the answer qubit. Okay, the answer qubit is in the state minus. Okay. All right, so let's write that down. How do I prepare that? So we have our X, the input qubit, or the question qubit, whatever you want to call it. And then we have the answer or output qubit, which is Y, which is prepared initially in the state 0. Then I apply our X gate, right, over here. And then I apply the Hadamard, right? And that gives me X and minus. Okay, everybody okay with this? Okay. At this point, we can apply the phase kickback identity or apply the oracle that we just defined, UF. Think of it as that matrix that we just wrote down. UF, we apply it to this input superposition. Okay, that is X times minus. So what happens? Well, UF will prepare X times 0 plus f of x or X 1 plus f of x. Remember, because this state input here is 1 over root 2, 0 minus 1. And therefore, UF acting on 0 will give me 0 plus f of x. UF acting on 1 will give me 1 plus f of x. Everybody okay with this? Yes? Any questions? Okay. If this step is clear, then hopefully the next step is also clear, which is that if f of x is 0, then this superposition becomes 0 here and 1 here, right? I mean, this state becomes 0 here, this state becomes 1. Which means the output is x times minus again, because this is 0 and this is 1. But if f of x is 1, then this state becomes 1, this state becomes 0. So I get minus state, but with a minus sign in front of it. So I get a minus sign times x times minus. which can be rewritten as -1 to the power f of x times minus. Because if f of x is 0, then -1 to the 0 is just 1. If f of x is 1, -1 to the 1 is minus sign. So this is just minus times x minus. So this is the phase kickback identity, okay? Or using the phase kickback idea. We kick the state of we kick the phase minus sign to the input effectively by choosing depending on whether f of x is 0 or not. Okay, that just again, this is called the phase arc. So it's a different way of thinking about the same oracle that we just wrote down, which is that instead of preparing that input as x and y, which are just classical states 0, 0, 0, 1, 0, 1, 0, 1, 1, what happens when one of the qubits is prepared in a superposition state? Well, the output now is no longer just 0, 0 or 0, 1, it has this extra phase in front of it. Okay. Of course, when it's just a global phase, it doesn't matter, but as we'll see in a minute, once we start introducing C0 gates and so on, this global phase immediately, like in the phase kickback, can start affecting the input qubit superpositions. Okay, any questions on this phase article, what it is? So just preparing the output with this extra phase on it, depending on the input f of x. Okay, and now we come back to our Deutsch-Jozsa problem. And remember, this is the Deutsch-Jozsa problem. So if hopefully by now this is becoming a little more clear. So you see, we prepared 1 and then the Hadamard. So that gives us the minus state right here. So this is the minus state. Okay. And then, of course, our input is now prepared with many Hadamards. So that, as we'll see in a minute, that's just the uniform superposition of all the bit strings. Then we apply our quantum oracle, which will create a phase on all the states, and that will give us our answer at the end. And let's go through that step. I didn't do the full Deutsch-Jozsa last time. I just did the Deutsch. I thought that because if I do it this way, then we can actually allow us to do all the other algorithms also a little bit more easy. So let me run through the calculation. So that was the algorithm, and now we'll work through the math. Which I think not get us to. Okay. So we have, instead of writing 0 and then an X gate and then a Hadamard, I'm just starting out with a minus state here, which you know how to do now. You just start with an X gate and then a Hadamard, and then you get our 0 tensor n, which is the n bits, times now we apply our Deutsch-Jozsa algorithm, which is Hn by UF. Okay. And then apply again Hadamard to the n, then measurement. Okay, that, and we forget about what's going on with the answer to it. Okay. All right, so let's work through what happens to every stage over here. Okay, so 0 tensor n with a Hadamard tensor n. Okay, that is just 1 over root 2 to the n, 0 plus 1 tensor power n, meaning I take 0 plus 1 on each and every qubit and I multiply it all out together, right? And the 1 over root 2n comes because there are n qubits. Okay. Well, this can be written as simply, if I just write out all the terms in the superposition, I'll get 0, 0, 0 plus 0, 0, 1 plus 1, 0 plus etc. up to 1, 1, 1. Yeah. So this is the uniform superposition of all the input states. We've done it for 2 qubits, just extend it to any number of qubits. It'll be pretty clear to you. If you just multiply by one more state, for example, you'll get the idea pretty straightforward. So this is the uniform superposition, and to make our notation a little bit less cumbersome, we're going to write this as 1 over root 2 to the n summation x belonging to 0, 1, n. Okay, so 0, 1 to the power n, the set 0, 1 to the power n consists of exactly this, all the bit strings from 0, 0, 0 up to 1, 1, 1, 1 for n bits. Okay, and this is the uniform superposition over all 2 to the power n of these bit strings. We have seen this before, but just remind you. And now I apply our quantum oracle, UF. And remember from our discussion just now, the effect of UN on this superposition is as a phase oracle. Right. That's what we just showed with the phase oracle for 1 bit. It's true for all n bits as well. We kick the phase -1 f of x onto the superposition. So whenever f of x is 1, we're going to get a minus sign in this. So you think of it as taking the superposition, and wherever f of x is 1, where x is the input string, wherever x is 1, it flips the sign of that superposition to a minus. So you can see the output superposition is now entangled, right? Because it's got parts that you cannot factorize anymore. Okay. So from this entangled state, we somehow had to extract information about f of x, which is what the Dutt algorithm does by now applying now again H tensor n. Okay, that's this output over here. Well, okay, that's 1 over root 2 to the n summation x belonging to 0, 1, n minus 1 to the f of x times H tensor n on x. So we have to ask ourselves, what is this state going to be? This is the difficult one in this superposition. It means we have to figure out H acting on each of these states. 0, 0, 0, 0, 0, 1, basically that Hn acting on those, what is that going to give us? Okay, so that is our next step. Any questions so far on these superpositions? I know the math is a little bit more heavy duty. The idea clear? This stuff is just notation, right? This is the actual superposition if you want to just write it out. And the action of the phase oracle is to put a minus sign wherever f of that bit string is 1. Okay. In the Dutt. Okay, so we need to figure out what Hn acting on x will be. Okay, so let's write it out as Hn, and now this x is a bit string, so I'm going to write it out as xn minus 1, xn minus 2, x1, x0. Okay, so these are all just individual bits, basically. Xn minus 1 up to 0, x0, each of these is a bit. So we need to know what is the action of H on any one term in this bit string. So because H, remember, this is H tensor n, so it's a completely separable operator, right? It's all like, tensor product of many H's. So if I know the action of H on any one of these bits, qubits, then I can just combine all of them for the full superposition. Okay? So H acting on x, well, it depends on x, right? If xi is equal to 0, we know this is just 1 over root 2, 0 plus 1. And if xi equals 1, we know this is 1 over root 2, 0 minus 1. Okay, to make again our notation compact, instead of having to write out all these cases, we make use again of a compactified notation, which is 1 over root 2, 0 plus minus 1 to the xi times 1. again, you can see when xi is 0, that's going to give me the plus state. When xi is 1, it's going to give me the minus state. Okay. All right, so we're almost ready now to calculate our full superposition. And remember, again, coming back to here, this is the state that we are trying to solve. Okay, so this part over here is just trying to look at this portion of it. So that's what I'm trying to solve over here. Eventually, whatever I get for this hn of x, I'm going to put it back into the superposition over here and see what we get. Okay. All right, so let's explore further this massively looking entangled superposition and what hn could be doing to this massively entangled superposition. We've written out what h does on any one bit. So all we need to do then is find h acting on xn minus 1 up to h0 acting on x0. Right? That's, sorry, not h0, just h acting on x0. So that's h acting on each term in that bit string. Okay. All right. So that is simply using our little more compactified notation, 0 plus minus 1 to the xn minus 1, 1 times the next term up to, let's go to say the term just before x0, which is 0 plus minus 1 to the x1, 1 times 1 over root 2, 0 plus minus 1, the x0. We're almost there. Okay, just bear with me on this last bit. So I'm just going to look at these two terms first. Okay, so that is 1 over root 2, 0 plus minus 1, x1, sorry, minus 1 to the power x1, 1 times 1 over root 2 times 0 plus minus 1 to the x naught. Okay. And if I write this out, I get 1 over root 2 squared. I'm just leaving it as 2 squared because then it'll be easy to see what happens to the n bit case. See, 0, 0 plus minus 1 x naught, 0, 1 plus minus 1 x1, 1, 0. Oh, ran out of space. Plus minus, okay, I have to write this on here. Just leave this part over here untouched because this is the final state. We want to put everything back. And right here. No, right here. Minus 1 x1 plus x naught 1 1. Okay, I hope the pattern is pretty staring out at you because you see, wherever there's a 1, I get a minus 1 to that bit. Wherever, see that? Yeah. Whenever I get a 1 in this bit string, I get a minus 1 to the power of that bit. Right? So whenever x naught was 1, I got minus 1 to the x naught. When x1 was 1, I got minus 1 to the x1. Minus 1 to the x1 plus x naught, for example. So the pattern then becomes, it's equal to, and each of these, now this is same, right? This is still 0, 0, 0, 1, 1, 0. It's the same as we had before, but I had to call this some new string because it's the output state. So I'm going to call these strings as S, okay? So this is a sum over all the n-bit strings S. Si, that is, S is now Sn minus 1. It's not, it's just to call it some new strings. It's still the same notation, it's still n-bit strings, but I'm just calling it S now because it's going to appear inside the summation. So this summation over here is 1 over root 2 to the n, summation S belonging to, again, all the n-bit strings, then minus 1 to the power of xi, but only when si equal to 1. Okay. So whenever one of these si's in here is 1, I have to add in a power of minus 1 to the xi. Okay. times all the n bit strings, which I'll write as Sn minus 1 up to S0. So it is the sum, the power up here, this power here is the sum of all values of xi such that Si equal to 1. So whenever I get a Si equal to 1, I put a minus 1 to the xi up here. Okay? And finally, that can be rewritten even more compactly as, if I consider the inner product of two big strings, x and s, this is just xn minus 1, Sn minus 1, plus etc. X1 S1 plus X0 S0. And you can see this inner product x dot s of the strings. For example, if Sn minus 1 is 0 and only S0 and S1 are 1, then you get just x1 plus x0 if S0 equals 1 and S1 equals 1, for example. Okay. So you can see that for any bit string that you want, this gives minus 1 to the power, say for example, x1 plus x0, whenever, for example, right here, x1 plus x0, whenever S0 and S1 were 1. Okay, so to finish our final story, now we need to put all this equation over here back in here, okay, into this expression over here, which I know this is a little bit starting to get difficult to follow, but hopefully you can rewind and watch this, or just if you have any questions, you can come and talk to me. So I put minus 1 f of x, and then for this now, I put in this whole thing and add in this term over here, where I write this summation over Si equal to 1 of xi as minus 1. I have summation 1 over root 2 to the n, s belonging to 0, 1, n. Okay, and minus 1 the x dot s times s. Okay, that's our final answer. So again, with a little bit of simplification, we write s, pull it outside, pull the s outside, and then inside we have 1 over 2 to the n summation x belonging to 0, 1 to the n minus 1 to the power f of x plus x dot s times s. Okay, so this is a very complicated looking beast, but in a minute we'll see that this gives us exactly the answer we wanted for the Dutt-Jozsa algorithm. So at the end of this, remember, in the Dutt-Jozsa algorithm, we only care about this state, right? This S. We want to know what's the measurement of 0, 0, 0, right? Because in the end, remember, we measure along the 0 basis. So you want to know what's the probability to measure, say 0. Okay. So probability that S is equal to the state 0, 0, 0. Okay. This is our question. Okay. Well, the answer is basically we need to project this onto the state 0, 0, 0, and we are going to get 1 over 2 to the n summation x belonging to 0, 1 n minus 1 f of x. Right? Because if s is 0, then this x dot s just becomes 0. Okay? All of them are zeros. So therefore that x dot s doesn't matter. Okay? So it becomes 0. So what is this probability? Well, if f of x is a constant function, then I can evaluate it at any value of x, which means let's say f of 0, 0, 0. Okay. Okay. It's equal to f of 0, 0. You have a question? Oh, sorry, I thought I saw it. Okay. Then probability is, of course, this square. Okay. Because it's whatever is the amplitude here, square. Okay. And remember, this summation is over the entire superposition, all the n-bit strings. So we just want one of those, the one where this term s is equal to 0, and that is this value. And if it's constant and this is, say, some value, so this gives me 1 over 2 to the n. And then since each of these is minus 1 to the power f of 0, 0, 0, I'll just call f of 0, okay, times how many of these are there? There are 2 to the n. So we see the final answer is just minus 1 to the power 2f of 0, 0, 0. Okay. Well, minus 1 squared is just 1. So this is always going to be 1. So for a constant function, the probability to measure this superposition in the state 0 is 1. And you can show that the probability to measure 0 for the balance functions is 0 because in this superposition, there will be an even number of terms that are 1 and an even number of terms that are minus 1. Because a balance function, remember, is 1 where half the outputs, or for half the inputs, the output is, say, 0, and for half the inputs, the output is 1. And therefore, you get an even number of, or the same number of ones and the same number of minus ones, so that cancels out. So probability to measure in the state 0, 0, 0 is 0. Okay. So if it's a balanced function, then we should always be getting that the probability to measure in the 0 state is 0. Okay. And it might be in any of the other states. Okay, it could be in, it could even be a uniform superposition of all the other states, as long as there's no appearance of the state 0, 0, 0. Okay, I know that was a lot, but this concludes sort of the discussion of Dutt-Jozsa algorithm and this idea of this, this uniform superposition, this kicking the face oracle outside and or taking this minus 1 to the f of x, and then similarly these types of identities where we find that minus 1 to the summation over all I equal to 1, si equal to 1 of xi is just written as the dot product. This is going to reappear in a couple more algorithms. So you'll have a couple more chances. But at this point, I'm going to stop and open it up for questions, or else we can go on to the test. Any questions? Okay. So there are. I'll start passing it out.
Yeah.